Hey everyone, my webinar is going to go over a little analysis of temperature at synanthropic bat roosts, and I'm going to do it using parametric and non-parametric methods. So I'm going to start with a background for my study, get into the objectives of this particular project, the data that I used, the methods that I used, and then transition into results and discussion. So just to give a background, synanthropic bats are those that depend on humans in that they are roosting in buildings. And here we're looking at Great Smoky Mountains National Park, where people, both visitors and employees, regularly report bats in historic structures during the summer months. Now this is the maternity period, mainly from May through August. And so we have concerns about not just threats to people, thinking about rabies and histoplasmosis, but also threats to bats from disturbance from people, which may have negative impacts on bat survival, both of the adults and the juveniles. And this is not well studied. It's not studied at all in the Southeast, and mainly what's been done in the past is most research has been conducted in Europe. And what they've found by examining roost selection through comparing the site attributes of buildings that are used versus buildings that aren't, they suspect that bats select building roosts hierarchically. So starting at the habitat patch level, we're thinking proximity to water, forests, or roads. At the structure level, we might be thinking about things like size, what materials the building is made of, and what features it might have, so chimney or louvers or shutters. And then at the microhabitat level, we're thinking things like airflow, illumination, humidity, and in this case, we're going to take a closer look at temperature. And temperature, we believe, it's likely that temperature is important to bat roost selection, as it has implications for use of torpor as well as juvenile development. So of the studies that have looked at temperature, specifically in the case of roosts that occur in buildings, when they compared roost buildings, so used buildings, to unused buildings, they found that roost buildings had a higher maximum temperature as well as a wider temperature gradient. Whereas other studies have found something a little bit different. These are mainly ones that have considered tree roosts and rock roosts, and they found that relative to unused buildings, roost buildings had lower maximum temperatures and higher minimum temperatures. So when the building is at its coolest, it's still warmer than an unused building. And when the building is at its hottest, it's still slightly cooler than an unused building. And this is logical, considering that, even if a bat may benefit from a very warm building, there still is going to be that ecological cutoff where it's just too hot and systems start shutting down. And they've observed this with a number of species, although it definitely is not very well studied. And with these other roosting sites, they took a look at ambient temperatures relative to roost temperatures, and this is not something that has been done explicitly with building roosts. So with these studies, they found that roost sites had smaller temperature gradients than ambient temperatures. So essentially the cavity that they were roosting in, or the rock crevice, was less affected. It buffered against ambient temperatures. The roost was less subject to temperature extremes. Oops. And so this leads to a number of questions about what is happening in the Smokies, since this is not something that has been looked at here. So we're thinking, how do buildings in the Smokies regulate ambient temperature, and are roost buildings in fact warmer than buildings unused by bats, which generally seems to be the implication from previous studies. So that leads to the objectives of this project, where we are going to compare building temperatures with ambient temperatures, as well as compare temperatures of roost buildings with unused buildings. And in general, our hypotheses are that buildings are warmer than ambient and have a lower temperature gradient, and roost buildings are warmer than unused buildings, also with a lower temperature gradient. So the data that we're using for this, ranging from the 15th of May to the 14th of August, last year I placed iButtons at a number of buildings and I set them to take an hourly reading. I put one at every roost building and then randomly selected a paired unused building within the same district, and that will make more sense when I show you the map. But we ended up with a total of 52 buildings with iButtons in them, collecting roost temperatures during the study period. And for my ambient data, I went to the National Climatic Data Center and got the Global Historic Climatic Norms data set, and they offer a daily reading of maximum temperature and minimum temperature. Unfortunately, they didn't have what I really wanted, which would have been something a little bit finer, maybe not necessarily an hourly reading, but something a little bit more specific. Obviously, this has implications for the outcomes of the analyses and not being able to compare exactly with the data that I collected, but we were able to, or I was able to summarize the hourly readings from the buildings so that we can compare them with the ambient temperatures for the two different sets of analyses that I'm going to get into. And there were 4 weather stations that roughly correlated with the areas where the buildings were, and that will make more sense in a moment. So here is the park. And over here we have the Townsend, well, it's known as the Townsend Weather Station, but it's really a lot closer to the Cades Cove area directly. And you can see that that weather station is going to be matched up with buildings that I found in Cades Cove as well as at the Tremont Institute. The second little group is a weather station near Gatlinburg, and there I have included the Elkmont buildings, the Sugarlands buildings, as well as the Twin Creeks buildings. And then here is Lufty. And over here is Cataloochee. The closest weather station is that one. Obviously that's not ideal. There wasn't anything better available. That's certainly something I will look into. So even though this isn't, you know, the weather station is a pretty good distance away, but it's about the same elevation, and it's the best I could do. So the first set of tests that I did, I was comparing all buildings versus ambient temperatures, and the ambient temperatures were those were matched with those weather stations. And I had 3 basic hypotheses about minimum, maximum, and the temperature gradient. Our null is that there's no difference in any of those between buildings and ambient. But my alternatives are that minimum daily temperature in a building is greater than the minimum ambient temperature. Maximum daily temperature in a building is also higher than an ambient temperature maximum. And that the temperature gradient in a building is less than ambient. So I'm thinking that the building buffers against ambient temperatures and therefore has a smaller gradient. And to get at this, I used 2 methods. I used a parametric test, the paired t-test, and the Wilcoxon sign rank test as my non-parametric test. So I'm going to get right into results. Again, these are differences between the buildings and their paired weather stations for the ambient temperature. And you can see in this table, these are the mean standard error for those differences. So that's the minimum, the mean difference between minimum building temperature and minimum ambient temperature, etc. For our p-values, well, first I should say that my data is definitely not normal, but I did it anyway just for comparison, and it's kind of interesting to see that the t-test came up with basically the same, almost the same types of results kind of throughout this, and that may be, I'm not actually sure why that might be. Maybe the differences were so large that even the fact that the data weren't normal, it didn't quite matter. But anyway, looking back to our hypotheses, that so these are all our alternatives, and we find that with the Wilcoxon, these they're wildly significantly different. So we can accept all three of them, mainly that building temperatures, both minimum and maximum, are higher than ambient minimum and maximum. So generally, we can say that there is evidence that buildings are in the Smokies are generally, at least the ones that I sampled, are generally warmer than ambient temperatures. And then that the temperature gradient within those buildings is smaller than the gradient of the temperature outside, or at least at those weather stations. So the second set of hypotheses, I was comparing roost buildings and unused buildings, so it's a different kind of pairing, but the statistical method still makes sense in this case. So again, I have 3 nulls for my maximum, minimum, and temperature gradient. And the nulls are that there is no difference between roost and unused buildings. So for my alternatives, I have that roost buildings are warmer, that the maximum and minimum temperatures are both warmer than in unused buildings. And then regarding the temperature gradient, I am predicting that the gradient within a roost building will be smaller than in an unused building. And again, I used a paired t-test and the Wilcoxon signed rank test. So getting into results, these are the minimum, maximum, and temperature gradient differences between roost buildings and unused buildings. So these are the two, the differences is what's being used in the tests, the paired t-test and then the Wilcoxon signed rank test, which are both based on paired observations. And relative to our alternative hypotheses, we can see it's just kind of interesting that the p-values are basically the same. Some of them extremely as close to 0 as possible, and others completely in the opposite direction. But we can say, and this is where it gets interesting, so the roost buildings, the minimum temperature at roost buildings we have evidence that it is greater than in unused buildings, so we can reject the null with relative certainty. And then the same thing for our gradient hypotheses. We can say that there is evidence that roost buildings, their temperature gradient is smaller than in unused buildings. But this second one here, with the maximum temperatures, we're seeing that there's evidence that roost buildings, their maximum temperatures are lower than in unused buildings, which is interesting and kind of makes sense. I mean, this is something that I'll have to look into moving forward, but we'll get to that in a minute. So just to overview, we have evidence that buildings in general in the park are warmer than ambient temperatures, both the minimum and maximum daily temperatures, and that they also have a smaller temperature gradient relative to ambient temperatures. And this is not only consistent with the previous studies, mainly those ones done on trees and rock roosts, but it also makes sense. I mean, being in a building and being in a building or in any kind of structure, whether it's a cavity or a rock crevice, it's logical that ambient temperatures would be buffered in some way. Not in every case you have insulation to take into account, and these are things that I'm going to be looking into with my big analysis, but the evidence that buildings are warmer and have smaller temperature gradients is not necessarily surprising. So now to our roost versus non-roost buildings. We have evidence that roosts have higher minimum temperatures than unused buildings, so when they're at their coolest, they're not quite as cool as those unused buildings. And we can infer potentially that this could have some impact on bats in terms of energy savings and metabolic cost. We also have evidence that the roost buildings have a lower maximum temperature than unused buildings. And this is something that I'm going to want to get into, looking at what those maximums actually are relative to what is the physiological limit, and compare with other studies, especially considering the species that are roosting there, and seeing if this makes a lot of sense, because even in these other studies where they found that maximum temperatures in roost buildings were higher than unused buildings, that may have been in other parts of the country where they have different climates than here in Tennessee and North Carolina. And this is something that we definitely want to take into account. And finally, roost buildings may have a smaller temperature gradient than unused buildings, so that ambient temperature is potentially being buffered a little better. This is again something that I'm going to have to try to incorporate, merge these two little sections here. And again, these three findings are consistent with some previous studies, but not all. It's really that maximum temperature finding that I'm going to want to explore a little more. So moving forward, end of next summer, I'm going to have another year of temperature data available. Moving forward, I'm also going to want to get some more specific temperature data for ambient conditions, both temporally and spatially. I want to get some ambient temperature that is closer to the buildings, and this may involve buying more eye buttons, which is very expensive. But if I can, I'd like to find just some weather stations throughout the Park Service that might have data that is more specific to these buildings and may have a finer time gradient. And I would also like to compare roosts and unused buildings by time of day, looking at daytime temperatures versus nighttime temperatures, as well as compare the building temperatures that I did find with those of other studies. And here are my references if anyone's interested. And also, if anyone has any advice on analyzing temperature data like this, I would really appreciate it. In addition, doing analyses like this in R, this was definitely, this was my first attempt at an analysis like this. And if anyone knows of any good packages that might help me out, or some post-hoc analyses I might be able to do, I would really appreciate it. And other than that, I look forward to seeing everyone else's webinars, and happy end of semester.